Hi, so in this tutorial, I'm going to be explaining a little bit about the convolution operation to give you a little bit of an idea of the theory behind the convolutional neural networks. So, yeah, the reason why we call the convolutional neural networks by that name is because we use this discrete convolution operation, which is a specific kind of linear operator that is used in some of the layers of the neural network. And in fact, in the book here, this is a deep learning book, and it gives this definition of a convolutional neural network. And in fact, it says that convolutional networks are simply neural networks that use convolution in place of the general matrix multiplication in at least one of their layers. So yeah, when we talk about convolutional neural networks, we mean that here we don't only have fully connected layers anymore. We have at least one layer which is defined by this convolution operation that we're talking about. And so what exactly is this? So here we have some general mathematical definitions, which are not super useful. In fact, the main useful definitions that we have here are the discrete convolution S here in equation 9.3, and this is what the convolution looks like for single dimension, but we're going to be using mostly image data, so this is the convolution is going to look more like equation 9.4 or 9.5. And so what this looks like is that if we have a two-dimensional image I as our input, which we're going to have a two-dimensional kernel K. And so what we're going to have is this convolution, which is this star operator here. I convolute K of ij is going to be equal to the sum over all m and n. So these are positions in the the neighborhood of on the image here of the image values times the kernel values. So what does that mean? So it means that the convolution out of position ij is going to be equal to the sum of applying a multiplication of the value in the image times the weight in the kernel in some neighborhood around that ij. So it's not specifically written out here, but this sum m and n here, what it means is try some pixel values around I and j, right? So maybe if you're going to have a kernel which is 5 pixels by 5 pixels, this m is going to be 5 pixels to the left or right of pixel I, and this sum over n is going to be the sum over 5 pixels to the up or down of pixel j. And then what we're going to do is, we're going to look at those the values of the image in those corresponding neighboring pixels around I and j, because the m and n. And we're going to apply the value we're going to multiply by the corresponding weight in this I minus nth entry of the kernel, or the j minus nth the I minus nth row of the kernel, and j minus nth column of the kernel. So so another way to visualize that, it's helpful to look at this figure here. So this figure 9.1, here we have the input image, which is just an image with 3 rows, or 3 pixels high, 4 columns, so 4 pixels wide. And the idea here, we have a 2 by 2 kernel, and so here the values of the pixel intensity values are represented by these letters from A to L here, and the kernel weight values, which we are eventually going to learn, are represented by these letters W, X, Y, and Z. So another way to think about that kernel the convolution operation that we were just talking about in the last equation is applying this kernel, kind of like sliding this 2x2 rectangular kernel that we see here, just applied at the top right over here. It's sliding that all around the image. So when we do that, we see, well, when we have the kernel applied to this first 2x2 grid in the image, what happens is, well, we just basically match up the corresponding weights, right? So here, what it says is that to get this output unit at this upper left corner, which corresponds to where the kernel is applied to the upper left corner of the input, what they do is we apply, we get AW, so that's the upper left entry of the input times the upper left entry of the kernel. Then you add this BX, which is the upper right entry of the input times the upper right entry of the kernel, plus EY, which is this guy times this guy, times plus FZ, which is this guy times this guy, right? So what it means is that you basically just match up all of the entries in the kernel to the corresponding entries in the input, and you multiply all of those guys together, add them all up, and then you get this the output unit that you would get here. So moving to another example, all right, so if we slide the kernel over 1 pixel to the right, so what we're going to do is we're going to be applying B to W now and C to X, and that's what we see here. It's BW plus CX plus FY plus GZ, right? So, then when you slide the kernel to the right again, it's going to be C times W and D times X, right? And so that's what we see down here as well. So what we get finally is a bunch of output units, which are defined by applying the same kernel weights to, it's kind of sliding that kernel around to different subsets or patches in the image, and applying those same kernel weights to the different pixel intensity values in the different locations in the image. So, yeah, that's kind of all I wanted to say in this first definition about what exactly is the convolution operation that is used in the convolutional networks. Thanks for listening.